Hello, I'm Mike McCulloch. Today, I'd like to talk to you about how we might be able to make what you might call a floating brick, like this, or maybe you could call it a hoverbrick, using quantized inertia. So, first of all, I'd like you to consider a shape like this, sort of a gingerbread man type shape with a hollow sphere on top, which is quite small, and a larger hollow sphere below. So the small one has a width of L, small l, and the large one is capital L. And the distance between their centers is d. And then consider what the 0-point field is doing inside this shape. So virtual particles, virtual photons are moving around at random inside it. But every time they go into the narrow circle here, fewer unruh modes will be allowed in quantized inertia, and so they will lose inertial mass. And every time they go into the larger area, they will gain inertial mass. So there will be a shift of inertial mass towards the wide end, and the whole thing should move very, very slightly, because it's a quantum effect, towards the narrow end. And this is equivalent to the M drive, of course, that I've already talked about. Now, what we can do here is this effect is incredibly small, but we might be able to make it large by shrinking this form, and then maybe we can have an array of them. So let's look at it using Heisenberg's uncertainty principle. So we're using the uncertainty principle, so that the uncertainty in position times the uncertainty in momentum equals h bar over 2. So for the wide end, we've got delta pw, so the momentum at the wide end, equals h bar over 2l, where capital L. And then for the narrow end, we've got delta p n equals h bar over 2 small l. And then the force you get from this gradient in the 0-point field that you've induced by the structure is given by, the force is the dp by dt, which is c, so the uncertainty in time is d over c, and the uncertainty in momentum is given by the difference between the momentum in the narrow end and the wide end. And this is a particular function of small l and large L. And if you assume that large L is 2 small l, then you can pare this down to a formula like this, where the force is mass times acceleration, which we already know, is 2h bar c over 2l squared. And we can rearrange this to make L squared the subject of the equation. So we get L squared is 2h bar c over 3ma. And the uncertainty here is the mass. So if we assume that the mass is just the shell of the two spheres, we can calculate the mass, and you can get something like 5 pi L squared times the density of the metal that's used times the thickness of the walls divided by 4. And then if you put this in for m, you can rearrange for L, and we get that L is the 4th root of 2h bar c over 15 pi, the density times the thickness times the acceleration. And the acceleration we want to overcome in this case is the acceleration of gravity, so that's just g. And if you put the numbers into this formula, you get a value of L that is 91 nanometers. So this means that if you want to make something levitate based on the 0-point field in quantized inertia, assuming quantized inertia, you have to shrink this gingerbread man down to the scale of 91 nanometers. So that is specifically the width of the larger sphere. So this is very similar to the M drive, but I guess a more solid observation or evidence for it would be the Casimir effect, where you get a force from the fact that the 0-point field is suppressed between the plates, and that pushes the plates together. That's the same sort of thing that we have here, but now we're translating it with asymmetry into a linear acceleration, which could be very useful. And if we could make a lot of these structures, 91 nanometers, and set them up into an array, then we can make a floating brick like this one. Okay, so I hope you've enjoyed this short, and I look forward to, oh yeah, I should say as well that I published a paper on this, and it's shown here, and I hope you enjoy reading that, and I look forward to speaking to you next time. Okay, bye.